Thank you. Thank you, Nick. Now the presentation is open for questions.
Thank you very much, Nick. Excellent presentation. I had a question about the nano indentation.
Right.
Do you have difficulty with the small indentation landing only on the filler particle or only in the matrix, or is it sampling?
It is sampling.
Kind of a heterogeneous region.
It is sampling, and I mean clearly in terms of number of indentations, then we're doing at least 30 per specimen to go on. Also, it is connected to a microscope, and you're right. It is an issue of where it is landed. So we're just going with the number of indentations to see what we get from there.
Nick, again on the nano indentation technique, it seems like you had some plastic deformation. And are you taking that into account somehow in the? I mean, it seems like you're beyond the elastic regime.
It is.
Does that get incorporated somehow? So this would have a slightly different meaning than an elastic modulus?
It could be. Is the technique that we're using, the continuous stiffness measurement technique, then we're going to a depth of 2,000 nanometers into the specimen. So as to if we extensively incorporated that, we haven't done any work towards that. So we almost take the values of face value. What we're giving.
You clearly did not have complete elastic recovery on your.
No, clearly not. No, that's.
We warmed you all up. It's your turn.
Nick, thank you for the presentation. One of the graphs you showed that irregular fillers provide a little higher elastic modulus compared to spherical fillers.
Yeah.
And what's your hypothesis for that? Because in theory, you shouldn't expect like any movement of the filler in the matrix once it's cured.
The differences, first of all, they were only with nano indentation, which is a more local phenomenon, rather than with the universal testing machine that is looking in bulk the whole of the material. So part of the differences could be because it's very localized, that effect. Now, I mean, you can argue that maybe irregular fillers, they're more packed in a certain way, it's difficult to move. Again, as you say, you shouldn't expect any movement of the materials in there. With the universal testing, we didn't find any differences. So they were both the same. So these minor differences, I'm not sure. It could be, my guess is that because it's a local nano indentation phenomenon there. There were some slight differences in the materials as well in terms of the filler size, but again, I don't think that would make a big difference.
One thing that I thought when I saw your data is that it's really hard to get like the same size of the same particle size. Like
well, for the fillers,
there's always
for the spherical fillers, it was the same particle size. For the irregular fillers, this was an average size quoted there. Clearly, it wasn't, and even for the distribution, when you have a bimodal distribution or trimodal for the sphericals, it was pretty good. So we were happy that the values given to us, and we looked at all of them under SEM, extensive under SEM, and the sphericals, they were okay. The irregulars, you would have a range of sizes. So
therefore, better packing.
So for the sphericals, we were able to validate that these were the actual filler sizes. For the irregulars, we noticed that there was a range of size and that these values that we're quoting, they probably are correct. We didn't do any extensive measurement by measuring ourselves the filler size of those. So we just assumed that what Evocolor provided us and gave us these values that they measured, they were okay.
Thank you.
I have a question for you as well.
Okay.
It regards wear. Okay, this is toothbrush wear. How about classic wear from occlusal loading? is that affected in the same way as your particle size, or is it going to be less or more?
Like to have a guess, what would I think it would happen on a...
Would it be, I don't know, we usually like to know if it wears off 100 micrometers per year,
Yes,
or
this
50
is
micrometers?
this is actually what we're doing now, and we're having two experiments. One is to see the effect of toothbrushing using a 3D optical profilometer. So with the 3D optical profilometer, we were able to measure the wear depth and wear volume for each material. So with the standard profilometer, we're not sure. Maybe the surface is smooth, but maybe it cleared off 200 nanometers, just removed together, and another layer which is underneath is also smooth, and it appears to be smooth. Or a material that only lost a tiny amount, but because it lost a tiny amount, it looks to be rougher than it actually is. So we're hoping with the 3D optical profilometer to quantify that and see how much volume we lost from each material on its purpose. So that's the first experiment. The second one is we now have, which we didn't have before, a chewing simulation machine. So that we're trying to simulate, instead of having the toothbrushing, having the simulation, so having an antagonist on the upper part, and see how that effect will have, and again monitor those changes with the 3D optical profilometer to see, first of all, the changes on the roughness, and secondly, the changes in volume as well occurring from that process. Is that what you were asking? But
Okay. I have another question next.
okay.
In the past, very convincing that coupling was important in mechanical properties when you have very large particle fillers.
Yeah.
Has that been shown again for the nano, that silination or coupling is still as important?
It is important. It's interesting to see what's happening in there. It seems to me that with the nano, you might have a whole layer being removed and taken off completely. So it depends. When you have the nanofillers, you have some of the nanofillers are actually inside the matrix as well. So it's not just independent. And possibly that could be the one of the most prominent effects of nanofillers, because they modify the refractive index of the matrix, and you can modify the refractive index of the matrix. So you can change the optical properties, not necessarily because of the filler size that you have, of the fillers that you have in there, but because you modify the refractive index of that one.
Nick, I do have a question about the elastic modulus. What do you think is too unique as a dentistry? There are some indications in dentistry where composites are somehow combating with ceramic. Ceramic has an elastic modulus of 68 gigapascal.
Yeah.
You have 60, you have 20 for resin composite. What does a dentist, if you have a selection of 10 or 20 materials, what do you recommend to select as a material with a high elastic modulus or a low elastic modulus?
Because the higher the modulus is, also the brittleness of the material will increase. And
yeah, I mean, obviously you can keep on increasing the modulus, as you say, and then you can end up with a ceramic material. Equally, if you just take away all the resin matrix and just have fillers, it will be higher modulus, but it will effectively be a ceramic. So as to what is the ideal value, I don't know what is the ideal value. My guess it will be, first of all, it depends on the application, what you have in there. It depends maybe on the volume of the material. If you look at the failure of the material, why does it fail? Most of the failures nowadays, what do the clinical results say? They're either from fracture toughness or shrinkage, which can cause secondary caries. So these two are what we're getting from clinical trials, the two most likely factors. How the Young's modulus can affect these properties, yeah, of course it can affect. And when you have the polymerization of the material at the early stages, then whatever is the shrinkage strain for that material and whatever is its Young's modulus, the combined effect will determine the shrinkage stress that you have and any problems that you can create in that area. It's difficult to say because it is a combined effect, and it can be influenced by the light curing unit that you're using. So you might have a material that has a stiffer material, but the way you polymerize it is not going to be that stiff, so it's going to change its properties. It depends on the volume of the material as well. So I can't give you a very clear answer, I'm afraid, but it's interesting to see the combined effect. And I mean, that's why I mentioned that there's like lots of different properties that need to be looked up to get a big picture. And it's difficult to have one material that fulfills all of the properties in a certain way. One of the difficulties in simulation in vitro is to trying to have combining those parameters at the same time and measure them. But this is some of the challenges for the new researchers to come up with new experiments.
When you plot this electrical modulus as a function of the volume percent of the pillars,
yeah.
And I see the slope change when the particle size changed. Have you tried to fit the rule of mixture and or Hash's condition to see if they agree with this theory?
Sorry.
There is a rule of mixture.
Yes. To see if that fits in what respect to see.
In the theoretical prediction.
Yeah. We didn't go to full extent to measure that. From the rule of mixtures, we noticed that these were pretty much the volumes that we could have in terms of there. So that was okay. But just to see the full theoretical extent, we didn't do it.
Mais alguma pergunta? Any other question? Okay, so thank you, Nick, very much for your nice presentation. So now we have to change to the next presenter.